value that I got for V naught was like the answer that you had multiplied by 2.
All right, well, I'll tell you what, I'm going to be honest with you, I'm not sure if it was 100 or 50, but let's just do this thing to make sure everybody's clear about it. All right.
Okay.
Now, you have your calculators, right? I'm saying that because you're going to get a problem, right?
Yeah, no, I left
I can't be, what?
I left mine at home. The one that can do everything, not just part of it. It's,
Well, that's unfortunate.
yeah.
All right, for this problem, we had a source voltage plus or minus Vs. Then there wasn't an RS, we're going to create one. Let's let RS equal to 50, just for the heck of it. Then we have a waveguide that it's going to be attached to. And this waveguide has dimensions A equals 2.5 centimeters and B equals 1 centimeter, right?
Yes.
All right, that's exactly what we had last time.
Yes.
Then we had a length here, and we had a ZL. And what was the length again?
9 centimeters.
9 centimeters, and it was air fill, which is nice. And ZL was what?
400.
400 ohms, okay. Now I worked this problem, and I'm very sorry I didn't post the right value of RS. I literally cut and pasted it, the values, and for some reason that one just didn't carry through. So if we're going to do this, the first thing, well, the frequent Vs is what again?
100.
100 volts, and at a frequency of
8 gigahertz.
so the very first thing we have to do is find the cutoff frequency of the lowest order mode, which is the 1 ohm mode, and see if in fact this frequency is above cutoff. And then you need the 2 ohm mode in this case because we want to see if it's below the 2 ohm. Follow me on this one? So the cutoff frequency is going to be what? Well,
16.
it's what?
C
C
over
over 2A, isn't it?
Right.
This is the 1 ohm cutoff, the TE10 over 2A. So that's 3 times 10 to the 8th over 2 times 2.5 times 10 to the minus 2. What does that come down to?
6 gigs.
6 gigahertz, right?
So 2.0 just double.
And the 2.0 is going to be double that. FC 2.0 will be equal to 12 gigahertz. This frequency is below that, and then FC, if you wanted the cutoff for the 01 mode, then that would be C over 2B. In general, what I'm using for cutoff frequency, the general formula is what? 1 over 2 square root of mu epsilon m over a squared plus n over b squared, where n and m and n are the mode numbers, right? This is just the general form for cutoff. So for this, what is the 01 mode's cutoff? C over 2b, anyone? B is 1 centimeter, right? Well, C is 3 times 10 to the 8th.
10.5 times 10 to the
15 gigahertz.
15, that sounds right. About 15 gigahertz, class? All right, so we're below the 2.0 in the 01, and we're above the cutoff frequency. We're operating in the 1.0 mode, correct? So after that, the next thing we want to do is get the characteristic impedance, Z0, for the TE10 mode. And that's going to be A to naught, because it's air-filled, over the square root of 1 minus the quantity FC over F squared. And I'm going to do this, and I'm going to call K equal to the square root of 1 minus FC over F squared. And that means FC in this case is going to be 6 gigahertz, F is 8 gigahertz, right? So this is the square root of 1 minus 6/8 squared, or really 3/4 squared, and that's going to be 1 minus 9/16. So it's 7/16 square root of that. What is that?
That's 0.66.
0.66. So that means A to naught here is equal to 120 pi. That means ZE or Z0TE is equal to 120 pi, right, over 0.66. And what do you get for that?
571.
Yeah.
571 ohms, right? Everybody agree with that? All right, now the next thing I'm going to go ahead and get is beta in the guide. Beta in the guide is going to be, this is along the length of the guide, this is the one we need, correct? And so that's technically what? Beta unguided times the square root of 1 minus F C over F squared. Isn't that right, class? All right, now we know what this is. That's K. So I can say it's beta unguided times K. And what is beta unguided? There's a lot of ways to do this. It's what?
Omega times square root of U epsilon.
Yeah, and I'm going to go do the one, but you can do it omega. It's actually omega square root of mu epsilon. You can do it that way. And times K, and that's 2 pi, right? Times 8 times 10 to the 9th gigahertz, and then the square root of mu epsilon, if it's air-filled, right, is 1 over c, correct, class? So just put c down here as 3 times 10 to the 8th, and that means beta guide is what?
110.82.
110, did you say?
Yes, sir, 0.82.
And that's equal to 2 pi divided by lambda in the guide, correct, class? Isn't that right? Remember, beta is always 2 pi over lambda. In this case, it's beta in the guide, lambda in the guide. It's lambda along, it's the length of the wavelength along the guide, right? And that's going to be what? So that means lambda in the guide is equal to 2 pi over 110.82. And what do you get for that value?
0.057 meters.
Say that again.
0.057.
0.057 meters. Anybody, you agree with me there, everyone? You might have done it a little differently. There's a lot of ways to get these values. This is the way I'm choosing to do it now. So that's 5.7 centimeters, correct? Now that means the length of this guide in wavelengths would be L divided by lambda in the guide, or it would be L is 9 divided by 0, or by 5.7. What is that? I'm getting it this way. This is the length of the guide in wavelengths in the guide.
1.579.
1.579? Hold that thought. 1.579 wavelengths, right? Now you can use that number when we do the beta L calculation. But you can also just subtract 1.5 from there. Do you all see what I'm doing here? By the way, what is it? What is 79 as close as it gets? This
You
might
do 1.5789.
89. Okay. You can leave that and there won't be a problem, or you can subtract 1.5 from that and get a value. If you subtract 1.5 from that, right, then you get 0.0789, and that's L. That would be the length of the guide in lambda divided by lambda in the guide. Then over here, let me do it right here. Now I need beta in the guide, right, times the length in wavelengths of the guide. So that's equal to 2 pi divided by lambda in the guide times, and then in my case it's 0.0789, right? Times lambda in the guide. The lambda in the guides cancel, and you're going to get a value for that. You can just put that in memory. You can give it to me if you want, but it's 2 pi times 0.0789. I can't tell what that is in my head. Anybody? And if you wanted to use the 1.5789, you can. What did you get for this?
.4957.
Anybody else confirm that?
Yeah.
I got that too.
0.49 what?
57.
57. All right. Now that is in radians. Make a note of that. That's radians, not degrees. All right. Now if you have that, now we can get the input impedance, correct, class? Well, we need, yeah, we can get the input impedance directly, yep.
So that's the beta L that you're going to plug in for tangent.
The
beta
argument
L?
of tangent.
Okay.
Remember, it's always beta in the guide and the length of the guide in wavelengths. It's the fractions of wavelengths that the guide's on.
So for the beta in the guide of the 110.82, why wouldn't you just multiply that by the length of the guide of 9 centimeters?
What say that again?
Beta in the guide 110.82. Would you not just multiply that by 0.09? And you get like 9.974 radians.
Yeah, 9.97 is the number I originally used. And I got the input impedance that.
Wait a second though. The beta, when you do the length of the guide in wavelengths, right? See, the wavelengths here cancel. This cancels this, so it should be the same value. Do you get this value for what you got?
I originally did it that way, but instead of 0.0787, I just left it as
You can.
I did 1.579. And then I got like beta L is 9.92.
Yeah, and what's that in radians? I mean in degrees. Well, I'm making a point here. Put that in degrees.
Should be like, shoot, 568. So I think
All right, now, you and I both know, every time you go a half wavelength, right? Or 180 degrees, you can subtract off that value. Are you all with me there? So if you would keep subtracting off, well, you could subtract off pi radians, m pi radians from that thing. You're going to get the same answer either way.
Okay.
I promise you will. Either way. I choose always to do this in wavelengths in the guide, though. I'm used to this. Always thinking in terms of wavelengths in the guide. That's just me because the lambda in the guide cancels, even though I used it to calculate that value. It will be the same. Do the tangent argument in both. You're going to see they're identical. So just for kicks, let me do it this way. So take the tangent, remember to be in radians though, of 0.4957 and give me that value. And then take the tangent of what you said, what is it, 9 point something?
Yeah.
9.92.
9 point what?
yeah, if you do it that way, it's 9.92.
9.92.
All right, now check the values on this. They should be identical.
Yeah, they are.
That's all you need to know.
Okay,
You
but
can use either one.
Sure. They're the same thing because here's what I do. In this case, I take 2 pi and I divide by lambda of the guide, and I have the length down lambda of the guide. What you did is forget lambda of the guide. You took the beta in the guide and just multiplied by L, right?
yeah, you get a slightly. If you do it that way, you actually get your solution. It's off by like just a little bit. So if you just do beta in the guide times L, you get like 9.974. Then you get.
I think we're dealing with this round off here because
Yeah, it's just a little bit
In
around.
your solution math, or I guess you used MathCAD, it shows 5.7 centimeters as the wavelength in the
But
guide.
there's extra
but it
numbers.
actually uses 5, 6, 6, 9, 8, and 3.
it rounds it up. Yeah, I mean it rounds it off. Yeah, just for display purposes. You're right about that. Either one though is correct. You follow me on this, guys?
Okay.
Either method. But the key thing is once we have this, now we've got to get Z in, right? And while we're at it, before we get Z in, let's get this reflection coefficient right here. So we need gamma here, gamma at the load, and that's our impedance that we use for this. So we have the impedance you're going into is 400, right? Minus that impedance 571 over 400 plus 571. What's that going to be?
Negative 0.175.
Minus 0.175. Now you have this down, don't you guys? We're going to need that, so we put it up there. Now what we need is, since these two are the same, Now we need the input impedance, and I think hopefully you got your calculators figured out by now. So Zn would be equal to Z naught TE10, that's that characteristic impedance. Then it's times ZL, that's the 400, plus J Z naught, times the tangent of beta L, and you can put in the argument tangent beta L and store it in memory, and then it's divided by Z naught plus J ZL tangent of beta L. I'm going to make one comment. Since you know beta L, you probably know tangent beta L. The beta, this is TE10 and this is TE10. The way I always remember this, I start with Z naught, it goes down, then it comes up and ends with Z naught as far as the tangent arguments. This is ZL, that's the L. I always know that the Z0, the characteristic impedance of the transmission line or the waveguide is the first term, and then it alternates. Z0, ZL, Z0. Down here, it's going to be Z0, ZL. And there's that J term if it's lossless. Are you with me, class? So when you crank this out, what do you get? I hope you got the same Zn as I did. Give you a Zn, didn't I?
Yeah, if you do it with that beta L term, you get 451.89
Plus
J 136.74.
0.89, 458.89?
451.89.
I'm sorry. And go ahead with the J term?
136.74.
Plus J?
Plus 136.74.
And you can give that in polar, but it doesn't matter. Do y'all get this, class? Did you get it? All right, your calculators, by this time you should have that. Now, that's important because now what we're ultimately after is voltage at the load, right? Correct, class? So once we have that, a couple other things we're after. I'm going to come here and do this part. So the voltage, pardon me. Now what I have to do is do the revised circuit. So I'm going to have plus to minus 100 volts here at a phase shift of 0 degrees, and then I put in my 50 ohms. We'll do it this way. And now I attach my Zn here. And that Zn is important, and the Zn is what's over there. And now I need to find this voltage, plus to minus, which I'll call V prime, and that's simply going to be 100 times Zn over Zn plus 50. And you can give me that value. I want to work this problem.
90.726 plus J 2.527.
2.527. And it's just about 91. It's a small angle. I'm not sure what the angle is on that. Can you give it to me in polar? Is it 91? Point something? Do your calculators have just a function, hit it, and it goes to polar immediately or not?
Polar, it's 90.76 magnitude.
90.76. Okay.
Pretty much
90.76 at an angle of even a degree?
1.6 degrees.
1.6 degrees. Confirm? All right. I'm going to remember my next step.
Divide by the E to the J terms.
Well, you're right, and I'm making this point one more time right here. Now, remember that V of Z, because the load is always at Z equals 0, in general is going to be some V0 plus times e to the minus j beta z plus the reflection coefficient times e to the plus j beta z, right? But the key here is that beta is beta in the guide. So you put beta in the guide now. Does everybody follow me on this? Remember, it's beta in the guide. The length It's really 2 pi over lambda in the guide. And it's important that you don't put just beta down there. Omega squared times square root of mu epsilon. Follow me, everyone? All right, now we have VZ at what? We have V at Z equals minus L. And that's this value. It's 90.76 at an angle of 1.6 degrees. And that's going to be equal to this, where Z is minus L. So really, what I'm going to do to save time here, I'm going to take this and divide it by, this will become a positive, so it'll be e to the plus j beta in the guide. How about if I just put beta in the guide times L, right? And it's going to be plus the reflection coefficient times, and this will be minus e to the minus j beta in the guide times L. And here we get a number, and I should have given you that number, but I don't know what value it was. I can look it up of RS I used. I thought it was 100, but I guess I might be wrong. Was it 50? Can you tell me what you get for this one?
This is for V naught plus.
Yes, this will be V0 plus, you're right.
Yeah.
And what do you get for that? The calculations are where it's the divide by these imaginary arguments that gets a little tedious. Anybody?
I got 99.103 at an angle of 144 degrees.
99.143?
103.
103, I'm sorry. 103 at an angle of?
144 degrees.
Can anybody confirm that? You got it? The trick is this beta guide times L. Make sure you have that consistent. Save that in the memory or write it down and just reuse it. And if you're unfamiliar with how to do this calculation first before you go right into the divide. Do it incrementally. Okay? Did you guys get that down? Did you get it?
I use 9.92 beta. Which
The
is
beta L, it won't matter which one you use. It's just round off errors where it's going to be a slight difference. You got the reflection coefficient. I think I erased it though. But you have that down, right?
right.
Did you get that value for V0, guys?
Slightly off.
Close. Did you have like 101 or 95, 98, 97?
99.07.
Oh gosh, yeah, that doesn't, that's too close, yeah.
But the angle's just a little off.
What is it, 144?
43.9.
No, this is 149, is that what you got? Don't worry, that's
144.
140, oh, come on, that's in the noise, don't worry about that. All right, now the last thing we're gonna get how do I get voltage of the load once I have this, guys?
That times 1 plus the deflection.
Right, in here for voltage at the load, when Z equals 0, the only thing you're doing is taking this, it's V0 plus times 1 plus the reflection coefficient, because the e to the j is really e to the plus or minus j0, which is 1. Do you agree with me? So what's that going to be? You've got gamma L, you've got that, so now you get the voltage at the load. This is for 50 again, not 100.
81.76.
81.76, go ahead.
At the same angle.
At
144.
144 degrees. Can y'all check and see if you got that? I got actually 2 more questions, all right? While we're still there, what would the current in the load be? That would be the current flowing this way. How do you get it?
I just divide 400.
It's divided by, and it's strictly real, 400, right? So that's just the voltage in the load. It's simply voltage in the load by 400, right? Correct? And so the 144 stays, correct, class? Right. And then what's my last step? If I want power in the load, how much power is dissipated by the load?
1/2 times the real
Right.
real part.
And I'm going to show you one thing. It's 1/2 times the real part of the voltage in the load, right? Times the current in the load conjugated. Now, this, what I'm about to tell you is important. You see how the load's strict real? It doesn't have any imaginary component, right? Anytime you have something that's just a resistance or strict real, just a resistance, you can get the power by saying it's simply 1/2 the magnitude of the voltage in the load squared over RL. You just take the magnitude of the voltage, forget the phase angle, because when you do a conjugate, it'll go away instantly. Square that value and divide by RL. So for our case, it would be equal to 1/2. Voltage in the load here is 81.76. So it's 81.76 squared divided by 400. And give me what that is.
It's off just a little bit from what I've got using the conjugate, but like 8.2 or 3.
It should be identical. Because when you conjugate, the only thing you're going to do is get rid of that angle. When you conjugate, you get rid of the 144. Follow me on that? Everybody? So say that again. What did you get? Oh boy. The bomb.
Let me make sure you just.
I got 8.33.
Did you get it?
Or 8.35.
Yeah.
3.5. And that's watts. And that's the average power. By the way, in my answers, what did I have for power?
1.703 watts.
All right, then I'm going to guess that my input impedance is different. I thought it was 100, but it may be more. I'm just going to tell you that. But this is the way you do the problem, and there, all right? Now, there's one other thing we have to do, and I think I asked this. What is the velocity here of energy in the guide?
C times K.
Exactly. Very good. So it's the velocity of light, c times k. And what is the group velocity?
C divided by K.
Exactly. I'm just saying that. You don't have to do the calculation. Do you follow me on this, class? The energy velocity is the one we care about, because that's how fast stuff is getting down the pipe, and it's very close to the speed of light. But if we had another mode, then both velocities, the velocities would be different, and that means we'd get a lot of problems, because one mode would be moving at a different speed than the other mode, and when there's superposition of those signals at the actual load, it would be garbled. Any kind of coherency, any kind of signal processing would be out the door. You could probably transmit power effectively, but that's about it. Are we good on this, class? Now that's in a nutshell the problem. I want to finish up this slab waveguide business. I know the theory on this stuff is boring, so I'm going to try to just cut to the chase on this stuff. When we have time, we'll do fiber optics. And last time, I was trying to get through it. I don't know how many of you looked at that proof. It's good one time to get an appreciation for it and why we're doing what we're doing. But a lot of this stuff, first time you look at it, you don't really see how come certain things happen. And let me tell you really with the slab waveguide, I'm just going to level here. Key thing is that only one mode propagates, just like with a regular rectangular waveguide. And there in the book, Dr. Wentworth says something to the effect, it can be shown that single wave mode propagation occurs for this condition. I don't know if you saw it. It's at the end of that section on the slab waveguide. I do have my book. Let me see if I can get this. By the way, I got a couple of AccuWeather alerts for a severe thunderstorm, either warning or watching this.
It'll probably be pouring by the time we get done with class.
Is that what it says?
That's what I'm assuming, just based off where it was at when I looked at it.
Yeah. It's supposed to be around like 3 o'clock.
It's supposed to be bad?
I think just heavy rain and wind and lightning and stuff, just thunderstorm, typical thunderstorm.
That's bad. All right, let me just tell you what I'm going for. I'm going to look at. I'm going to do TE and TMO, but on page 404, equation 7.95, that's the key thing. That equation for single mode propagation. Y'all see that at the end of the section?
Which one?
It's
7.95.
7.95. It's single mode in a slab, and that's the key because you only want one mode. You follow me, class? Now, when we do this, I'm going to show you something. So when we have a slab in general, I'm going to go through this one more time, but you don't actually need to write this down. If you pay attention, that's all I ask you to do, because some of this is a recap from last time. If we have a separation distance A, this is the actual fiber, so the waveguide. So I'll just call this eta guide. And eta is the characteristic impedance. And eta guide is equal to the square root of mu in the guide over epsilon in the guide. All right. Now out here we're going to assume we have air. And air, of course, has eta equal to 120 pi. All right. Now, how many look at this actually in the book? The graphical discussion goes something like this. We're going to assume that we have a wave coming in. It hits, bounces here, hits here, bounces here, and hits here. Now, this is the angle of incident of that wave. And it's bouncing, so it's coming this way. He says this is E naught right here. It hits, and when it comes off, it has he calls it EA actually, and then he calls this is going to have the reflection coefficient magnitude. Well, really, let me do it this way. The wave hits the surface, there's going to be a reflection coefficient that's mode dependent, right? And really, it's dependent on eta 2, eta 1. And I'll get to that in a second, but just appreciate what I'm trying to do. It's different for TE versus TM. Please understand that. So I've got an electric field, say it's coming out of the board, it hits here, it comes down. At this point, the value is going to be the reflection coefficient at this surface times E naught. Then it moves all the way down here, right before it hits here, it's going to be the reflection coefficient times E naught, and then would be times e to the minus j, and it would be beta here in the guide, but it's beta unguided in this region. Call it just beta unguided, times this length. This is labeled A, this is labeled B. So it's times LAB. Can you all appreciate this so far? This is just a phase change, right? Let me draw it a little larger so you can appreciate this. Right here, the value of the electric field just before it hits there would be this value, gamma, times E naught, and then it's going to be times e to the minus j, and would be beta inside here unguided, not beta guided, times this length, which would be LAB. Can everybody appreciate this? This is the change in phase, the wave it goes through. Sounds like it's here. I don't have anything to do with it. Anyway, now it hits here, right? So now it's gamma squared, right? When it hits right here, and it's coming back this way. So then it moves from here, and remember what I was saying is, for coherency, what you want is, if I look at just this phase front, I want this to hit, slam down here, come here, and these 2 points have either the same phase or differ by 2 pi times m in energy. That was the argument I made last time. Now, that means it hits here, and that's what it is on the other side of this. And now it moves through here, so it's also going to be times, you're going to have to add to this length, not just LAB, but then it's going to be LAB plus L, and call that C, BC. I'm trying to be consistent with the way the book did it. Y'all see that? Now, after that, you have to realize that this gamma term has a magnitude of gamma that is mode dependent if it's TE or TM, and it has a phase. So it says e to the j phi. There's some phase. It could be 0, and it could be just a value of 180 degrees, which would make it minus, but could have a real and imaginary part. So it could be somewhere between 0 and 180. Y'all follow me in this class? We don't know. It really depends on a few other things. Now, I know at this point, right here, this has to be in phase, right? And remember this, let me write this. I can write this as magnitude of gamma squared times e to the j 2 phi, that phi is associated with the phase angle there, times e to the minus j beta unguided times LAB plus LBC. Just one time work through me on this. You all see that the phase is always in these exponential terms, the j terms. So the way this works is this: I find the phase, and it doesn't matter which one I make minus or plus. In his book, he takes this is plus and this is minus and sets it equal to 2 pi n. But it really doesn't matter. So if I take beta unguided times LAB plus LBC here, and subtract 2 phi from it, it has to be equal. Phi is going to be the phase angle associated with that reflection coefficient. That has to be equal to 2 pi m. Now m is the wave number. That's the whole idea. It's going to have to be in phase. So if it hits here, they're saying there's a phase point. This phase front is moving this way. That sounds like rain. So it hits, bounces, and it moves. Now, we didn't say if it's TE or TM, right? And there'll be two different values we get for where this solves it. And I'll just tell you right now, the thing is you have to get this phi right here in terms of the angle theta. Are you with me on this? There's also a stipulation that I didn't say. You have to assume theta I is going to be greater than the critical angle. What's the critical angle?
It's all reflected.
Everything's reflected, right? How do we always calculate the critical angle? Snell's law, right? We use Snell's law, we set the sine of theta transmitted equal to sine of 90 degrees or 1, right? So we can calculate the critical angle. So this is an assumption that this angle here that it's hitting at is greater than the critical angle. Now we go into the reflection coefficient. We'll do the reflection coefficient for the TE mode. By the way, TE means that the electric field would be pointing out of the plane right here and bounces, right? I don't expect you people to remember this. All right, I don't. But you at least have to have an appreciation for it. That's why I'm doing what I'm doing. So the reflection coefficient for the TE mode, I always tell people to do it this way. The impedance you're going into, well, the impedance I'm going into is N naught, isn't it? Right? That's the second impedance, isn't it? That's where it's going as this thing's bouncing. And it's always going to be minus the impedance you came from. And I'm just going to call that eta guide. Then it's over eta naught plus eta guide. I know that for a fact. Now I know the argument here, if it's TE, all right, it's the impedance I'm going into times the cosine of the phase angle of the media, the first media. Do you follow me on that? So this is times cosine of theta incident there. This is cosine of theta incident. And this is cosine of theta transmitted, right? And this is going to be cosine of theta transmitted. Do y'all remember that, guys? Hope you do. One other thing I want to say. It actually doesn't have to be greater than a critical angle. Let me just tell you why. Because if this thing, even if it loses some power, say it's not quite the critical angle, it's below that, still on these bounces, if there's a very small fraction amount of power lost, you'll still have coherency here. Do you follow me? Even though the wave will decay in power the further down the sky you go. Are you with me, class? So there's a lot of things about dielectric waveguides that are much, much different than metal waveguides. With a metal waveguide, nothing can propagate out of the guide. Nothing. Everything's contained within it, right? With anytime you have dielectric, it's not the case. Remember that. Except for fiber, because they literally put a cladding there that's black. It can't penetrate. But for this particular kind, it can. Now, these are characteristic impedance, right? I want to show you what he does. Remember, eta, in general, is the square root of mu over epsilon. And that can be rendered as the square root of mu naught over epsilon naught times the square root of mu relative, epsilon relative. Do you all follow me on this? Now, I want you to understand something. Since eta naught here, and eta guide, eta naught and eta guide, if I break it down, all have this term, right? Don't they? I can get rid of that term. Do y'all agree with that? And just put the things in terms of the character or the relative permittivity and permeability, right? Let's do it a step further. Let's assume in the guide mu relative equals 1, period. All right, same as air. Then what this equation will become is gamma TE equal to, this is going to be simply equal to, and also, by the way, since eta naught is air, right? I'm going to have 1 over the square root of epsilon relative of air there. Won't I, class? Let me just write this down. When we go through the whole 9 yards, we're going to get 1 over square root of epsilon relative of air times the cosine of theta incidence minus 1 over the square root of epsilon relative of the guide, I'll just call it epsilon relative g, times cosine of theta transmitted over 1 minus the square root of epsilon relative of air times cosine theta incident plus 1 over the square root of epsilon relative of in the guide times cosine of theta transmitted. Please try to understand. I want to get rid of the mu naught epsilon square root term, period. And since mu relative is 1, it cancels everywhere, top and bottom of that equation. Do y'all agree with me here, class? Now, last point I'm going to make right here. What is the square root of epsilon relative of air? What is epsilon relative for air? 1, isn't it? It's about free space, so you can get rid of this one. That's what he does in his book without saying it. Now I have this equation. I'm going to go a step further. I'm going to go, well, I could actually leave it like that. But really, what is the square root of epsilon relative in terms of an optical term? Isn't that the index of refraction, right? Square root of, so that's equal to the square root of epsilon relative. So now what I can do is this. I can replace this term here, right, with just what? Index of refraction of the guide, which is more appropriate because guides work at optical frequencies. So now I'm just going to put n, right, of the guide, and I'll make this n of the guide. That is the index of refraction. Remember, the index of refraction, the symbol is the small letter n, and it's equal to the square root of epsilon relative of that material, people. How many remember that from physics and from our other discussions? Y'all remember that? You've had index of refraction when you had optics in physics, right? Now, if you're not real familiar with it, just realize the only thing it is the square root of epsilon relative, and it's used, that is a common term used with anything that is glass or glass-like. All right? When you go to a optometrist or ophthalmologist or an optician, well, an optician won't know, but an optometrist or an ophthalmologist will know that what they're really doing, they're making glasses for you, doing any kind of lensing. They're really just using Snell's law, and they get a highly polished surface, but the material they use for the lens, glass, is silicon dioxide. That's all it is. It's sand, really. Molten sand that they fuse. I mean, you probably can get glasses made of other substances. By the way, what is the index of refraction for glass? Anybody? Do you remember what it is for silicon? What is it for silicon? Epsilon relative is what? 3.94? Remember this? Silicon dioxide in the back of the book. What is epsilon relative? Look it up right now. And because you can get impurities in there, and that will change it. But for silicon dioxide, what does it say? SiO2. This is another Acula. Hey, what is it?
All I see is pure silicon.
SiO2. Oh boy. Glad we're inside, guys. Oh, poor dog.
Would be a different, just glass.
Yeah, what is
Of
that?
tin.
All right, that's epsilon relative, right?
Yeah.
That's undoped glass. Square root of 10 is what, 3.1 or something? About 3.1, right? Now, that means that what you've got is, with those glasses you're wearing, it's about 3.1, the index of refraction. Is it a tornado warning or anything? Well, keep your breast in case something else happens.
So there was light extracted with fine oil.
hits us, we'll know what we're saying. All right, now what I'm going to do is this. Since that's the index of refraction, I'm going to leave it like this, and I'm going to do one other thing. I want to get rid of this cosine. You're not going to like this. I do this one time just so you appreciate it, all right? I don't expect you to recreate it. You got to appreciate it. So we use Snell's law for that. And Snell's law says beta 1 times sine of theta incidence equals beta 2 times sine of theta transmitted. That's the general form, isn't it? And we know beta in general is equal to omega times square root of mu epsilon, which is equal to omega times square root of mu naught epsilon naught times the square root of epsilon relative mu relative. Now, here's my point here. That beta term, omega times square root of mu naught epsilon naught, occurs on both sides. Do you all see that? The only thing I care about is the square root of epsilon relative, right? Which is the index of refraction. Do you follow me? Now if I put this in terms of the index of refraction, it would be, well, beta 1, this is region 1. So I'm inside the guide, and it's banging around like this. So here, I would say this equation then becomes index of refraction of guide times the sine of theta incident equals index of refraction of air times the sine of theta transmitted. You all see this, class? All right, what is beta of air? What is the index of refraction of air? 1. I'm good. The more you say that, the more likely you are to retain it. Now I have this. Follow me? Now in this book, if you follow the proof, he squares both sides. And now I have index of refraction of the guide squared times sine squared in the guide equal to sine squared of theta transmitted. Now sine squared of theta transmitted, see, here's what we want to get. From this, we want to get theta t, or the transmitted angle, in terms of the incident angle, so I can plug it in there, and preferably a cosine argument. You all see this? We'd like to get cosine of theta transmitted. If you've read this, you know how to do it. Well, the sine of theta transmitted, sine squared of theta transmitted, isn't that 1 minus the cosine squared of theta transmitted? Right? Sine squared plus cosine squared is 1, isn't it, class? So 1 minus cosine squared of theta transmitted is sine squared of theta transmitted, right? Then what I do is I multiply everything. Let me get rid of that middle term. I multiply both sides by minus 1. That makes that minus, that plus, and that minus. Got me? Then I take minus 1 to the other side, makes it plus. So now I have 1 minus that is equal to cosine squared of theta, right? Here's where you got to be careful. Whitmer's book doesn't do this. Now when I take the square root of both sides, now I get cosine theta transmit equals the square root of this, but it's actually plus or minus the square root of that. Right? Whenever you take a square root of something squared, it's plus or minus that value. Correct, class? He doesn't do that. That's an important fact you have to put down. That's the cosine of theta transmit, which means now I can go up there, or I can go better yet here. And if I just look at this term for 1 second, I have cosine theta transmitted divided by n guide is equal to, and then I have the square root of 1 plus or minus the square root of 1 minus mg squared times the sine squared of theta incident over ng equals cosine theta incident. Do y'all see what I'm doing here? Or cosine theta transmit, pardon me. Oops. Divided by ng, pardon me. Divided by ng. Can you all see what this? I'm up to something, just bear with me, right? Now at this point, one thing I can do, if I look at this, you all see how I can take and divide 1 over ng in the top and bottom there? Right? And so what does that make this? If I divide, it would be ng squared, so now I get 1 over ng squared and it would get rid of this ng squared here. Please understand what I'm just trying to do is show you that now this term reduces to this term. Are you with me? Remember, this is the key right here. So now if I take this right here and replace it by just this, just watch. Now I get this, and he does do this. I have cosine of theta incident, and I have minus or plus. Remember, I'm going to put minus there, but then I'm going to do this. I'm going to put minus, then it could be plus or minus. Right here, the square root of 1 over the guide's index of refraction squared minus sine squared of theta incident. And downstairs here, it's going to be cosine of theta incident, and it's plus or minus right here, square root of 1 over ng squared minus sine squared of theta incident right here. Now I have everything in terms of an incident angle. And here's the trick I'm about to show you. You're not going to like it. When I take a look at this, right here, I can factor out a minus 1. Just watch this. Matter of fact, let me do what I'm about to do right here so you understand. If I have the square root of, follow me, a minus b, that's equal to the square root of minus 1 times b minus a, isn't it, class? Right? Y'all agree with that? Square root of a minus b is minus 1 times square root of b minus a. Do you agree? Well, what's the square root of minus 1? Plus or minus j, right? Times the square root of b minus a. Now, in Wentworth's book, what you're going to see he does here is in this argument, he's going to switch the positions of these two. He's going to put the sine squared first, I think, right? And then he puts the eta values. He has a ratio of 81 to 82, doesn't he, class?
It's index of refraction.
Yeah, I mean, not 82. Index of refraction 1 over 2, right? Well, that's what I have here, but I'm assuming it's air on the outside. He doesn't. So what he does is get this. Now he's going to get the sine squared minus, and it'll be 1 over 8, index of refraction of the guide squared. That's going to be the same thing down here. Sine squared. And then he's going to have a j out front. Now I'm going to get rid of this plus or minus business because it doesn't matter which one you take if you're consistent. This will be a minus, this will be a plus, and then there will be a j here. Are you with me? This is for TE. Now, the only thing we care about is not the magnitude of TE, we care about the phase. Do you follow me? If you look here for a second, I need to tell you about this. If you have something where I have a minus jb over a plus jb, think about a as like cosine, b is like square root of sine squared of theta incident minus 1 over the square root of n guide squared. So that's the form it has. Can you all see this? Well, if I want the magnitude and phase of that, what do I have to do? There's one singular thing of that a minus jb over a plus jb. Do you remember? Complex conjugate, right? So if I multiply both of these by the complex conjugate, right? And what would be the complex conjugate of this? A minus jb, wouldn't it? Because what do I get downstairs? Then I get a squared, right? I get plus jba minus jba, they cancel, and then I get plus b squared, right? So I get b squared, I get a squared plus b squared downstairs, and what do I get upstairs? I get a squared, right? And then I get j times j is minus, a minus times a minus is plus, so it's a squared minus b squared, and then I have minus j times 2ab here, don't I, class? Just bear with me, I'm just trying to show you how he gets the final result. Do you follow me on this? So think of A like you would this term. Think of B like you would this term, right? What's the phase of that? Well, do you agree that A squared minus B squared is strict real? You all agree? And this is strict imaginary, isn't it? So what would the phase be? It would be the inverse tan, plus or minus, by the way, the inverse tan of 2AB divided by A squared plus B squared. Do you all see that? So what it amounts to is this phase angle here is going to be tan minus 1, and it has to be a plus or minus here, of 2AB, so it's 2A cosine theta incident, B, which is the square root of sine squared theta incident minus 1 over n guide squared over, and then it's going to be A squared minus B squared, so it's cosine squared theta incident. I don't know if he shows this theta incident, and then it's going to be minus B squared minus sine squared theta incident plus 1 over beta guide squared. Now in his book he'll reduce this because you got a cosine, now where is this? He's going to go through some permutations, and he's going to have this phase angle here, if you look there. He'll have it equal to tan minus 1, and it should be a plus or minus, but he doesn't have that here. And then he's going to have the square root of sine squared of theta incident minus 1 over eta guide, which you'll call eta 2 over cosine theta incident. Can you all see that in there where he has this is the phase angle for the TE mode?
Yes, 2 tan minus 1.
You're right. And what he's doing is manipulating this formula down to a point where it's got a magnitude and phase. Do you follow me? Now you can manipulate this by itself. You don't have to do what I've done. But that's all he's doing. He's getting a magnitude and phase. The thing I have to caution you about is this. Whenever he replaces cosine of theta t by the square root of something, it has to be plus or minus the square root. Just remember that. It has to be. And he doesn't show that here. Anyway, he's going to get a phase. And this is the phase he gets. And it's by manipulating those things. Now, actually, does he have eta 1 over eta 2 here squared? Eta 1 for all, eta 1 is air. It's 1. So I don't even bother with it. Are you with me? And then he should have a cosine theta incident down here. Now, that comes from manipulation down here, and quite frankly, I think that'd be a little much to do, but he'll have something like this too shown there. And see, his problem is, you see how downstairs that's not strict real? It's got real and imaginary parts. So the only way you can get a phase is doing a complex conjugate of it. And then if you do a complex conjugate, what you have to end up doing is manipulate this thing some more. Oh, the 2, he's got the 2 out here, right? Class? Okay. You don't have to worry about that manipulation. You have to worry about that understanding that it's going to be the phase associated with this. I'm going to tell you one thing right now. For this one, that phase angle is usually going to be either 0 or minus pi. It's not usually, I mean, you can get differences in there, but it's usually one or the other. I got to be careful about that. Okay. Now, last thing. So hopefully have an appreciation for this. The very last thing I'm going to talk about, oh my goodness. Didn't realize it was that loud. I gotta give you a quiz. Here. This is a straightforward quiz. Do me a favor, separate yourselves by at least one open desk. This is closed book, closed notes, but you can use your calculators. You're gonna thank me for doing that problem in the beginning. I'm sorry. I didn't do this whole thing.
You just started. We just finished up slab waveguide.
Yes, we didn't. I didn't get to the single mode, but I'll give you the equation for single mode. That's the only thing you have to know.
I was just asking for the video just to make. I always like to.
Yeah.
Know what we're talking about.
It's basically we take the waveguide, and then we did. I'm trying to do slab waveguides and give you an appreciation for how to do that. And you don't have a good calculator, huh? Well,
I can do everything until you get to E0, or like E0 plus.
I don't have a good calculator with me. But you're used to an 89?
84. That's what he has.
Who has?
The other guy.
When you're done, can you?
I got an 84 if you want to use it.
You got 84?
Yeah.
Oh, okay. He has an extra calculator.
Fantastic. Do me a favor, put your name on it first.
I don't know how good the batteries are, but they should hold up.
Thank you.
Just make sure you write your name legibly. And this is a straightforward one. It's really just making sure that you did that homework.
Dr. Baginski,
Yeah.
should there be a frequency